Hi, and welcome to episode 14. So, where I left off, we were just getting to the point that we almost had a simple peak optimizer working, except that it doesn't work. The code is written, the code runs without crashing, but when we look over here where we expect to see things like this getting optimized out, it turns out that it's still here, right? There shouldn't be a lot of simple situations, not every case we're going to be able to do this, but in some situations where we're doing some actions that don't do a consume, we're expecting to see that get optimized away by pulling forward actions from the next state that hopefully does contain a consume, or pulling forward, more accurately, actions from every state we can deduce until we find a consume, or until it's no longer simple to do so, right? And so especially cases like this where there's just one input, we would expect a lot of time for that to get removed. Like here it's not removed, here it's not removed, and I mean, I don't know how many, some of these like this we would not expect to get removed, because in order to remove this, the system would have to split this up into multiple transitions, and we're trying to make a peak optimizer that for now only does simple stuff without splitting up transitions to make it work. We could do this quote-unquote perfectly, and at least perfectly in the sense that we make sure every single transition has a consume in it, if we were allowing ourselves to split up transitions. But for now we're trying to keep these to optimizations that are optimizations both of the number of states and transitions. That is, one or both of these things, neither of them should ever be increased by any of the things we're adding, and to justify adding it, it should at least decrease one of them in normal cases, which so far has been the case for things we've done, but this hasn't done anything for some reason. So let's take a quick look at that in the debugger. So, I kind of want to look at one where I already know what I expect to see happen. So, not root. Let's look at number, Z number, F number, Okay. There it is, string. That's the one I want. Now, string has a few transitions in it, 5 to be exact, after the optimizations that have been applied so far. I think that's fewer than I started with. I think we looked through this at a previous video and the number was 7, so kind of neat to see that it's been shrinking, hopefully correctly. What we want to do now is look for the transition that should be going into this check here and coming back into the loop. Okay, so we ended up in there. So I'm not sure which transition we're on. Let's take a look. It goes back to root, and its activation actions, it has one action before it transitions, and that one action looks like it's an emit type, right? Because it has an emit rule here. So, whoops, sorry, didn't mean to, that probably popped. What we want to do is we want to start just looking at what this does and figuring out why it doesn't look like it pulled anything forward. So a couple possible reasons would be that one of these checks isn't working. Like, we're looping through the transitions of the destination state, and the thing that does the subset check just never succeeds. I already see what the problem is. Now that I'm looking at the code that's about to run, I can see what's going to happen. So the problem was I wrote this in a bit of a hasty way. I don't want to go to double break right away just because the state, the transition I was looking at didn't work, because I'm actually trying to see if any of the transitions work. So this is more like found action extension or something like that equals false. If this happens, then found action extension equals true, and we break out. Then what we'll do is say, if we get to the point where we have not found any action extensions, then we'll break here, and we won't need the double break anymore. So I was doing the double break inside this loop here, but it's actually more like I only want to do that if all of them fail, not if any of them fail, right? So there's a slight alteration of the flow of logic there, and hopefully that gives us better results. So if I go to state string now, you'll notice this doesn't do any reduction of states and transitions. What this has done was to skip transitions that were not going to do anything useful, and here it is. So this is pretty cool. This right here was what we were looking at before, that did a transition to root and an emit. So it did like emit, go to root. Now it's doing an emit, consume, set flag, go to white space. So what that means is, I'm guessing this thing here is a new line character, and before it was saying, hey, I saw a new line, I want to let root decide what to do with this. But what root said it wanted to do was consume the new line and then set a couple of flags and go to the white space state. So now we're pulling that operation forward into this position, and we are skipping the extra transition to root. So whether or not we did a lookup table or a control flow based implementation, this would be an optimization. In the control flow version, this just saves us an extra jump, basically. We would have had to do a jump instruction here to go to the root state. It would have done some actions and then done another jump to go to white space. We're just doing those actions right here and then jumping to white space, giving us a maybe slightly longer program, at least so far, but saving us an extra jump in the execution path, right? And the extra instructions aren't that big. There's just 3 of them. For a lookup table, this is even better, because every time we do a lookup table that doesn't do a consume, we essentially have to do all the lookups again. And so really, for a lookup table to really succeed, we want to get to the point where every single state always is guaranteed to have a consume in it. And so this peak here would be a move towards that, but we would really start getting the payoff for this once we could say, look, consumes are a guarantee. We can actually remove them from action lists because we've optimized action lists to the point where they always have a consume in them, right? We might still need to leave them in terms of where they occur, but we would no longer have to ask, does a consume occur here? So this would give us the ability to basically say all of the actions that happen up here get marked as not being, like, we can remove consume and say, like, we do like a pre-emit, post-set flag, post-set flag. Really, set flags are fluid. They could happen anywhere. It just matters whether we emit before or after, because emits that happen before a consume have a different length than emits that happen after a consume. Same would be true of setting the delimiters. So delimiter marking would also be something that would need a pre and post on the consume, so that we could tell if it needs to use the new or previous index, right? But besides that, what we also get for this is, in both cases, now that we've done this, there's a potential that we can simplify transitions and states again. Now, it's not necessarily going to work in this state machine. Well, I'm not sure that it will, but if you think about it this way, what we just did was shortcut several spots where things were like jumping into other things, right? And potentially skipped. We basically said whenever we pull forward, do this behavior pull forward thing, there's a chance that in the act of pulling forward, the fact that we are changing our new destination to the next destination in the chain has the potential to skip over a state and thereby leave it completely out of the graph. So just to be sure that we're working on the most optimal version of our machine, like state machine, that we've optimized it down fully, what I'm going to do is say I don't think we need to simplify transitions again. That just does the thing that shrinks the number of transitions down. We haven't done anything that would lead to redundant transition information, but we do want to do the thing that simplifies states again. We don't need to do this part here that transfers state actions to transitions because that only needs to happen once and there'll never be actions on the states again. Now, it's possible that we'll get new redundant transitions because of this. So maybe we want to do that again here too, but I'm going to be sort of doing these things one step at a time to see what we get. So yeah, you can see we actually reduced the number of states by 2 when we added that, and what happened to our transitions? So we got rid of 2 states, and 234 became 231. So 2 states and 3 transitions just by, after doing this round of optimization for peaks, doing another round of simplifying states, right? So every time we simplify states, we remove states that are no longer reachable, essentially. And different things like skipping past thunk states is guaranteed to remove a lot. This wasn't guaranteed to remove any, and yet it still got to, which is really cool. So I'm kind of curious to see which 2 have been removed. So in order to answer that question, I think what I'll have to do is just walk through it's hard to say what would work. How will we determine which states are gone? What I guess I could do is make a thing that says, instead of printing transitions, let's make a different print option that does a print on states only. And so that'll work like this. It'll say, here's the number of states. I'll keep the thing that gives me a number of transitions because that's not really distracting my ability to interpret this situation, but I won't do anything past printing the name of each state, right? Okay, so I didn't switch to that over here. Print my states. Okay. So there's our states before we optimized out 2 of them by doing this peak optimization, and now after, it's hard to say. I should see them side by side is what I should do. So here's the optimized one from before. Whoops. Yeah. I think we're done with you for now. I'll get rid of that. So there's the optimized one, and here's the unoptimized one. Now we can see these side by side. So comment line here is on line 50. Comment line here is on line 51. So there's one above me somewhere that got removed. Pre-L and pre-L align. So between pre-L and comment line, universal 8 and universal 8 align. So between universal 8 and comment line, get delim, they align. Comment block, do not align. Finish delim. There it is. So this state here got skipped. This is the first one we find. Get delim, finish delim is no longer in the state machine after this. Where's the next one? So it looks like if I wanted to test this, what I'd have to do is let's add in a dummy so that this aligns here. And now these are aligned again. And we can binary search the rest of this for the second one. So these are obviously off by 1. It looks like we must have... Wait a minute. The root and stage are both missing from right here on this side. Did I not copy it all over, or did we really actually get 2 more gone than I thought? Or like, should be only 2 missing, but I see 3 missing. Was that 69 wrong? So let's figure this out. So 1, 2, 1, 2, right? And then, so if we subtract 2 from 71, we get 69. Let me take out the dummy over here. The last line here is 69, and we subtract 2, we get 67. Yeah, what am I missing? I guess one of these stages must still exist even though the root got removed or something. So we must have optimized out this route, I guess, and kept its stage. That must be what happened, which is kind of cool. That means that anyone who was calling to that route was able to look through the route and find out what the thing that came after the route did in that case, and skip straight to it, which is pretty cool. Yeah, that's pretty cool. I think with a little bit more work we can actually optimize out both of these routes as well, because these routes are basically only exist as entry points into into sort of automatically generated code. So it's not handwritten, rather it's generated off of an operator set, and so it's kind of like, in order to structure the logic correctly in isolation, I create an entry point state that other things, when they want to use that logic, always go into it without consuming any characters, so that the root can actually do the logic on what happens with that character. But that means we actually have a pretty good case for optimizing these routes out by saying, hey, anyone who wanted to go into this route didn't really want to do a peek for any particular reason. It was just that the way that we wanted to automatically generate some of these things led to making it easier to do a peek into that, so that it could do the dispatch on the input correctly itself. But usually we only have one spot where we're doing that, and that's where we say, hey, check and see if you see any of the characters that belongs to this operator set. If you see one of those, I don't know what to do with it, but dispatch it to this guy, and he will dispatch it to all of the individual continuations off of it. Well, that's nice and all, but since we're already going to have a spot where we say, if you see any of these characters, peek at, don't consume them, but go to this thing, and then there's going to be someone else who has that set of characters splayed out as one handler per character, we might as well just say, get rid of that extra state, pull those handlers into the one spot where we were calling that entry point, and there we go. So this is something we talked about last time already, which is how we would go about doing that without having to break our back doing a full thing, and while maintaining the rule that we don't ever let transition numbers go up in the name of shrinking the state number, or vice versa. If we go back to main here, how do we do that? Well, there's another peak optimization we can apply. And the other peak optimization we can apply is kind of thinking about it from the other side down. So in this one, what we did was we said, if we have a peak operation that easily fits into its destination, then pull that one destination handler forward into the transition. That way we don't have to split any transitions. But another way we could look at it is, if there's a peak handler that goes into a state, and it's the only handler that ever goes into that state, then that state is redundant. Right? That state only exists to be the destination of this peak. So anytime we have a peak handler that doesn't consume its input, and it goes into a state, and that state doesn't have any entry points besides that one peak handler, what we can do is say, alright, that state is overcomplication. Really what should be happening is the transition handler, where this is happening, should just assume all of the transitions that are in that state that are subsets of the cases that can actually even trigger that state in the first place, right? That state probably has a bunch of extra, like a fallback handler in it that we don't even need, because the fallback won't be possible, because we're gonna inherit the fallback from the state that was peeking into this one originally, and so that can go. The state itself can go, and the transition that did the peak can go and get replaced by all the transitions that were in the other state. So the idea is, we're not splitting this transition as much as we're deleting it and borrowing all the transitions that used to be in the other state and culling them down to just the relevant subset that the original transition that we got rid of would have actually used to trigger that next state, right? Does that make sense? Hopefully that makes sense. So we're going to do optimize again. I'm going to call this remove, actually, because it already has remove peaks without creating transition splits. This is going to be remove peaks into single entry point states, right? Okay, let's see if we can figure out how that logic needs to look. We want to be able to print the before and after, and then we're going to want to be able to run these optimizations again after that. Alright, so first of all, what we want to do is we want to say something like, you know, we had this idea of back references before. So I want to see if we still have that and if we can update it. So what I kind of want to do is I want to be able to clear back references and reset them, right? Or rather what I should say is I want to say for each state, before I do this part, yeah, got it. I'm going to call this, I'm going to rename this to opt update state back references. So what update state back references does is it makes sure that these back references know all of the places in the entire state machine that can enter into a particular state. So each state has its list of transitions, but this is the backwards transition list, basically. It's the list of transitions that enter this state, not the list of transitions that can occur once you're in this state. So what we want to do is have this call clear that information so that it can update it, right? So for each state, what we are going to do is just block 0 struct out the state back references, right? And then we'll create a new back reference list right here. Okay, so I'm updating the back references. Now the next goal is include that in this right here. So remove peaks into single entry points requires updated back references on the states. Now, the other question is, why is this not just a part of transfer state actions, right? That's just an example of me being dumb. That should be hard-coded in right there. Because that just was me basically having a hidden coupling where this requires its back references to be correct so that we can do this transfer. And, you know, having to know that you call this before this every time you want to call this is silly. I mean, yes, we could avoid redundant work if we were going to call this twice, but we never are. It's just better to do it in the way that makes it easy to get it correct rather than to do it in the way that allows me to optimize it in the future and risks being very confusing. So now we want to do the thing that does the single entry point optimization. So the back references are now correct. So what we're now interested in is looking at all the states and finding every state where that state only has one entry point. So its back references has one node in it, and that back reference is a peak, or rather the back reference doesn't have any consumes in its action list. If that ever happens, then we have a case where we can eliminate that state and replace the old transition in the in its parent state. In other words, take the transition we were pointing at and say you're removed and replaced by this list of transitions that I already have, culled down by some factors of this, right? So to get all that in there, we might have to reconfigure some stuff because although we have a back reference to the transition, we don't actually have a way to go from a transition to the state that owns that transition. So we might need to implement something to do that. And then additionally, we are going to want to have an easy way to remove a transition and replace it, so this might need to become a doubly linked list. So there might be some reconfiguration that needs to happen before this works, right? I say we get on that part first, because this part here is the high-level stuff, and this part here, we're at the beginning of the video, we might as well get into the weeds at the beginning so we can get out of them by the end rather than vice versa, right? So this is going to become a doubly linked list. and it's going to have, whoops, parent state. And then whenever we make a transition, good, there's only one spot where we ever do that. We have a state pointer for it already, good. And so all we have to do is say, when you make a transition, let's see, what are you doing here? You're not sure what any of this code is. Why would I even want this? You can just go away. I think what's happening there is we still want some way to enable field checks, but I'm not actually sure we do. This is a special case type thing that we probably want to not like restrict to only very basic features. We're not doing this part yet. What we are doing though is we're looking at how we construct this. We are here setting the destination state. We are here setting the activation list. Activation list, destination state. Up here is the condition. Yeah, I figure I'll just put this right here at the beginning. So the parent state just needs to be the state, and then whenever we push this on, it's not it's not a singly linked queue anymore. It's now a zero-ended doubly linked list. So we need to push it on like that. And I want to take a look at all the places where this and this get mentioned, in case there are any other places where we are manipulating the list and need to update the type. Like right here, for instance. There we go, that should be correct now. Good. Again. Okay, I think we've got them all. Hopefully that does us some good. So now we are holding doubly linked lists of transitions rather than singly linked lists of transitions, which will be handy for the situation where we want to remove one out of the middle without having to iterate through the whole thing and then replace it with a bunch of other ones, right? So that's cool. The next thing we want is I guess the next thing we want to do is write the high-level code. I can't think of... I thought there was another thing that we needed to look at, but I am forgetting all of a sudden. So, maybe not. Maybe that was actually not that hard. I'm not sure. Why don't we just run it real quick to make sure... Yeah, okay. Nothing has changed. Okay then, let's do this. So, we are looking at a state's back reference list. So we need a iteration over transition putter nodes. We're looking at the state's back references, and before we even go that far, we want to see if the count on this is 1. So this only applies to states that have one back reference. If that is the situation we're in, we don't actually need an iteration, we just need to grab the node because, you know, I mean, hopefully that goes without saying. And then I can grab the pointer off of that, so I don't even need that. I can just say, like, source transition is what you get when you look at the pointer on that node. Okay, so we have our source transition, and then we can grab the source state because we now have a way to go from transitions to the states that own them. And so now we have a source state and a source transition, and that means we're going to be able to manipulate this transition if it turns out that it's a peak, but we need to actually determine that. So how do we determine if it's a peak? Well, we want to say if the condition set, or rather, if the, what is it? It's like the action list contains consume. There it is. So we want to look at the source transition, the transition going into the state we're checking right now. And if the source transition into this state here, I just want to do a quick sanity check because maybe this restriction is not necessary. Maybe any state with a single entry point should be optimized this way, and I just want to see if the logic works out for that. So the problem would be if we did think of it that way, then it's possible that I have a consume and the next one has a consume. So there would be actually two cases where this concept works, and that would be if I have a state with a single entry point and the handler going into that entry point does not do a consume, then we can do this work, because now we are talking about pulling all of those transitions up into the place where, to replace them, and whether or not they have consumes is besides the point, because the one that was originally there didn't have a consume, so we are guaranteed to only get one consume per handler, right? On the other hand, if the thing that has the transition in the single entry point into this state does have a consume, but none of my handlers have consumes, or none of the handlers that I'm going to keep after I, intersect with the cases that it transition into this state, if none of those have consumes, then this would actually still work. The rule is we just have to make sure. Wait, would that work? Because you wouldn't do the... No, it wouldn't work. No. So it only works if the source state and the source transition doesn't have a consume. Because if it has a consume, then the state we're looking at does actually add some work by doing a discrimination on the input, right? So it's adding work by discriminating on the input. The only time it doesn't add work is when the person transitioning into them, the transition into this state doesn't do a consume, thereby meaning it didn't do all of the discrimination work it could have done, and it can actually assume the responsibility of doing the discrimination on the input that the state would do. Yeah, that's true. Okay, so we do need to check this, for sure. So if this does not contain a consume, then we want to do this optimization, right? We've now determined that the optimization is appropriate, and we want to apply it. So to apply it, what we have to do is say, all right, so the source transition has a condition on it, and we want to take that condition, and I guess the other thing we need to do is, it's possible that we have a single entry point state that doesn't have a condition set. And it's also possible that we have a single entry point transition that's, doing the transition into the single entry point that doesn't have a condition set. So we're not quite sure we can apply this yet. What we also have to do is we have to make sure that both the state itself and the transition into this state, neither of them can be doing delimiter matching. They have to all both be condition sets. So we can do this pretty easily by saying, look, the source transitions condition kind needs to be one of these condition sets, and it can't have a consume in its activation list. Then what we have to do is say, okay, this state that we're in had better not be doing a delimiter match. So this state does delim match equals false. And then the rule is that if a state that contains a delimiter match only contains the delimiter match and nothing else, so we can check this by saying that the state's transitions first condition kind equals delim match would make this true, right? And so what we basically want to do is say we're only moving forward if this situation here is not the case, right? if the state we're on does not have a delimiter match like this, we're good to go, assuming the type checking has applied. It might be that there's a delimiter match later, in which case that's a type checking error because these are supposed to be the first and only in their state if they exist. And then if that goes through and we only have one back reference, then we know that we need to look at, then we're eligible to be a single entry point optimized state. We need to see if we actually are a single entry point by looking to see if, no, this says we're a single entry point. This says that we don't have a delimiter match in our, like, we're not a delimiter matching state. This here says that the source transition is also not a delimiter matching state, and I guess we could represent both of these the same way. So these both want to be condition sets, and there's not already a consume in the source transition, which means that the state actually does have to do discriminatory work. Okay, so if we're in this condition, we definitely now want to apply the optimization. So now it makes sense how we apply the optimization. We do a loop over the transitions of the state we're in. This state has a transitions, and the idea here is that some of these transitions are going to get removed. So we need to write the loop this way, and we're going to prepare to build a new list. Right, and at the end, we're not going to actually take that new list and so something else we can do here is, instead of doing this here, we're actually going to do this like this. I mean, we could, the way it was written would have been correct, but we can kind of get get this for free this time. We're going to mark all states as excluded, and then instead of trying to do this iteration across all states to find which ones are included, what we're going to do is actually invert the my drink got caught in my throat a little bit. Now I'm coughing. Okay. So we're going to invert this. We're going to mark all states as included, and then if we do this optimization, we can mark the state as excluded, right? And the way we do that is by saying that you are not optimized in anymore. So, as I said, once we've reached this point, we know we're applying the optimization, and the optimization is going to remove this state in particular. So we're taking that one out, and we're building this new list. But the new list isn't for the purpose of replacing the transitions in the state. This state is getting ignored. This new list is for inserting into the source state's list of transitions over top of its original transition. So we're going to be able to remove one or more transitions, you know, the one that we're replacing plus any of the ones that don't survive the process we're going to do here and end up in this list. And we're removing this state every time this optimization triggers. So, how does this work? Well, we want to we want to start by, we can modify and place this transition here by saying the new parent state for every transition in this list needs to become the source state it's going to get moved to. The new condition for this list is what you get when you intersect this condition you already had with the condition from the source transition. And the reason that makes sense is we're saying, look, this source transition is the only way to enter into this state. So any of the things it never handles would never actually be handled by this state either. So we can just throw those away. Now what we're going to do is say, okay, when we do that, we might end up with an empty set. So we're only going to do the rest of the work that's relevant if this is not the empty set, right? So if it's not the empty set, we change this. Now the activation actions, what needs to happen there? Well, what needs to happen there is different than pulling actions forward. Rather, what we're doing here is more like pushing actions like ahead, like pulling actions forward in time, or pushing actual actions backwards in time. Forwards in time. Forwards in time doesn't mean backwards in time. That's confusing. So I've been calling it pulling actions forward because we're looking at the next thing and pulling it forward, but it's actually pulling it back. That's confusing. I gotta rename that. Pull behavior backward. Oops, sorry. Behavior forward becomes behavior backward. Okay, so pull behavior backward means take a state, this transition and this transition. This is the one we're keeping, this is the one we're copying, and we're pulling backwards into this one. Okay, pulling forwards is going to go the other way. We're going to say this transition is getting removed, but it happens before the one after it. So push its behavior forwards. There's pulling behavior backward, meaning take it from a future transition that we know is going to happen and pull it backward into the transition that we already know is happening first. And then the other one is to do it the other way around, to say, hey, we know that this action is going to happen and then these actions, and we want to push these actions forward into those ones and keep those ones and throw those ones out, right? So, here, I gotta adjust my camera a little bit. Yeah, that'll work. So what's going to happen is when we are doing this peak here, the time comes where we want to take and push the actions forward. So pull behavior backward. I'm going to change behavior to right, actions backward. And then there's opt transition push actions forward, which is also just going to look like this. So we want to take the things from the source transition and push them forward into the transition that comes later. And I'm going to just rename these to A and B, I think. So there's pull actions backward. Here's push actions forward. Push actions forward have the following properties. We don't change the destination state when we do this. We do change the, we do change the action list, and we change the action list in the following way. This still applies if the copy of A's action list is if B has a 0 action list and A does not, we just copy A's action list and store it there. If B does not have a 0 action list, and okay, so that's actually a bug up here. So this is assuming that, yeah, this should be B actions. This right here is a bug because B might not actually have actions to pull backward, right? And so this would actually trample over, like it'd be sitting next to a null pointer, but then it'd be sitting last to a null pointer. So we need to do an extra check here to make this correct in the case where B doesn't have any actions. Right? And the same thing is true of this. So in this case we're taking A actions and pushing them forward. So we only want to do any work if A actually has any actions. But when we do this, what we're going to do is say that the changes need to go like this. The last thing in the B action list is irrelevant. The last thing, okay, let me think this through. So A wants to be at the beginning of the list, so A actions.last next needs to become the B activation list actions dot first, right? A last next becomes B first, and then the A activation actions last, right? So A actions dot last. So actually what needs to happen here is that the activation actions from B needs to move its first pointer up to the A actions first pointer. And then finally we can add the A actions into there. So this is the opposite of this. This is taking B and putting it at the end of the list of A by manipulating these pointers. This is taking A and putting it at the beginning of B by saying take the last node in A, point its next pointer to the first node in B, take the first pointer in the B list and set it equal to the first pointer of the A list, thereby subsuming into the B list all of those things we copied right here, and then finally add that into that so that we have the right count. Okay? So that pushes actions forward. Now when we push actions forward, what we're not doing this destination state thing. Is there anything else that needs to happen? Not doing the destination state makes sense because the B's destination state is the one we want to preserve in either case, and the idea of pulling actions backward is that A is getting kept and B is getting ignored. So A is getting rewritten to do what B did, and B is getting skipped. Here A is getting skipped, and B is being done in place of both of them. So we're pushing these actions forward, and so the B destination state needs to stay. Is there anything else about the transition that needs to stay? We could argue that the parent state from A needs to get pushed forward to B, but I feel like that's a decision that I want to leave up to the code calling this, because, you know, who knows which of these two states, like we have two different transitions, who knows which state of the two of them is the one getting eliminated? It's hard to say. It could be that we're throwing this away and moving this into its state, or that we're throwing this away, deleting its state, and linking the previous guy's state into this guy's state, right? It's impossible to say who's keeping it. So parent state isn't really like destination state. So I don't think we do anything to push that forward. Conditions, yeah, okay, that's good. So these need to be condition sets, which is going to be big long code. So we're going to pull that down here like we did before. So if the new condition set is non-empty, we push forward everything from the source transition into the transition that we just pared down its conditions, and it still has relevant conditions. So we are going to keep this transition. We are modifying its actions so that it represents the actions of both of the transitions together. Finally, what we need to do is we need to push it onto the list. Once that's all done, we've got a new list, which is all of the transitions that need to be used to replace the source transition inside the source state, right? So to do that, what we want to do is say, it's a little bit confusing, so I kind of want to take a minute to think this through on Scratch over here. We're dealing with a linked list, so it's doubly linked, and the relevant parts are these pointers go both ways like that. I'm going to write it this way to show that it's two separate pointers. This is the one that we've marked for replacement, and it can be in one of the following three states. It can look like this. It can also look like this, in which case it holds a null pointer to this, right? It can look like this, in which case it holds a null pointer like that. Or it can look like this, in which case it holds that one null pointer, right? So 4 states. I think I said 3, but I meant 4. And we are going to, in any of these 4 states, want to replace this with a chain. Now, that chain, if it's empty, would imply that something had gone wrong. So the chain had better not be empty. But the chain could contain just one thing, could contain a lot of things, contain anything other than 0. So how do we want that to look? Basically, we have a first over here, so we have F, and we don't know what's in here, and we have L, and these are guaranteed to have null pointers here and here, right? And so now what we want to do is say we don't know what's going on here, and that could actually be a deceiving picture because it could also look like this. Okay, simplest code possible to replace the star with this or this, depending on which case we're in. We're in one of these 4 states and one of these 2 states. What needs to happen is this needs to go into where the star is if that's the state we're in, or this needs to go into where the star is if this is the state we're in. So we have the following things. These pointers here need to get replaced with these pointers here no matter what. These pointers here need to get replaced with these pointers here no matter what. Then, if these are non-zero, they need to get replaced with L, and if these are non-zero, they need to get replaced with F. Okay, so 1, F and L pointers replaced with stars pointers. 2, maybe I don't want to do them in this order, but this is the order in which I have discovered which things I need to do, and then I'll figure out what order I can do them in without losing the information with the pointer swizzling nonsense. If prev of star exists, its next needs to be F. Prev needs to be L. And there we go. So, I think we can do them in this order here, right? If the source state, or the source transition, and then we have to do all this because I'm not using sentinels. So here's a concept that's maybe a little goofy, a little wacky, a little wild. What if I did a sentinel and then removed it afterwards? So what I could do, instead of all the ifs and nonsense that are going to make this complicated, is what if I said rewrite this into this in all cases by replacing the null pointers with sentinels for the time being. How would that work? I would create a sentinel node and point its next to the first, point the first previous to the sentinel, take the previous pointer of the sentinel back to the last, and the next pointer of that to there. And then when I'm done, all I have to do is use the sentinel to undo the pointers into the sentinel. And in the meantime, the code that writes the insert of that list there can simply set 4 pointers. It's actually more work. Okay, not worth it. Kind of a neat idea, not worth it. If the source transitions, let's see, if the next, if its previous exists, so if the source transitions previous is not 0, then the source the previous transition in the chain needs to see first. If the next transition exists, then its previous pointer needs to see last. Finally, the first pointer's previous needs to see the source transitions previous, and the last pointer's next needs to see the source transitions next. Then what we can do is take the count. The count lives in source state transitions.count and add in this count here. Right? I think that does it. I think that inserts the linked list we built here into the linked list that this already has. Do we run? we do run, the number of transitions has gone up. So we said we could never allow transitions to go up, and they have. Well, why is that? Well, this particular optimization isn't complete yet, but what it's doing is it's taking points where there are single transitions and replacing those single transitions with potentially multiple, and in fact often a bunch of them. Because if we look down here now, we'll see that root, which didn't used to have this, now has handlers for colon, plus, minus, less than, greater than, equal, bang, and, or, star, modulo, left brace, right brace, well, left curly brace, no, left brace, right brace, left paren, left bracket, right paren, right bracket, semicolon, tilde, twiddle, hat, okay, etc., right? What I would like to see is that's what it looks like when we've expanded everything out with all those new transitions. I want to show you again what the root state looked like before I added that optimization, and I want to see it for myself because I am curious and I enjoy seeing these things work. So, somewhere around here, here we have it. See this? This transition here, which had this complicated union of a transition case to begin with, transition to oproot. This was the only spot where we transitioned into oproot, and that oproot, if we go look at it, is the big one down here. The big one has all these handlers. Right? So if our thing has worked correctly, we have a question mark, a comma, but this will have gotten dropped, and it'll have gotten dropped because it does not do anything that was actually ever possible to reach, because the only person ever entering this state right here only supports these 22 particular input situations, right? So if we go down to the very bottom and look at the second state for the root, because remember I printed it twice, so the second state for the root, we now have those three which were present in the previous one, and then all of these operators that were present in the oproot up above, the comma, and then this left arrow thing gets included still, but that's from the old root. The old root had that. The other thing is gone, so the comma is the last thing that got pulled up in there. So what we've just done is we basically skipped past a state. But the problem is, and the reason we haven't seen an optimization in our numbers, is that state is actually still in the machine too. So all we have to do to see our optimization kick in is discard all those states that are now excluded, and what we should see is we should see our state number and our transition number go lower than what they were before. There we go. So now the number of states is down to 65 from 67, so we got 2 more by doing this, probably both of the oproots, honestly, and we got our transition number down to 229. So for comparison, where we started was 231, so that's 2 more transitions removed. Which doesn't make a whole lot of sense to me, honestly. I want to look into that a little more. I should be seeing at least 3 transitions removed based on what we saw already, because the transition into the state that got removed should be gone for both of them. So both of those should be gone, plus the fallbacks for both of them should be gone. And the fact that they're not seems strange. But if we come down here, we can see that there are now yeah, so now this doesn't go to oproot anymore, it goes straight to op stage. So I bet there are no oproot states anywhere in here. Yep, so the oproots got completely removed. This op stage here is the one that got referenced up there. It takes a pound sign to emit this, or it takes anything else back to root. Right, okay, makes sense. Cool. So, some interesting thoughts. One thing we could do that might be a little cheeky and fun is we're going to depend on which optimization route, like which output generation method we're going to use. Lookup table acceleration wouldn't actually benefit from this, I don't think. Although it might actually, because there would be a way to reduce states, which always helps the lookup table version as well. So maybe this is just an idea that would help in either case. Is we have stuff like this where we have, look at this, equal sign, equal sign, equal sign, equal sign. Each of these looks identical. Now, I'll bet you if we were to see what we're emitting here, it would no longer look identical. And what we would see is that each of these differs in one way, that they differ on what they emit when they see an equal sign. And in every other way, they're the same. They're probably all emitting Lexer errors if they see anything else, or possibly a different token. There could be that there have two different parameters, this token and this token. Not sure. That's probably actually more likely. I would be surprised if it was Lexer error now that I say it out loud and think about it. But you know, we still have this case where it's like, look, same behavior in every situation. We see an equal sign, we get one emit, we get a consume emit, and go to root, and anything else we get an emit, go to root. So it'd be kind of nice if that was all one state, but then we would need some way to know what to emit when we threw that information away. So there's still a lot of room for fun optimization ideas. The way we would have to optimize that down is by saying these parameters here would get stored into a lookup table, and we would have some kind of like additional state. So we would have our primary state number, like our primary state code that tells us what state we're in the like consume loops. But anytime that the consumption rules look the same. So which thing we would, under what condition we do the transition, where we transition to, and whether or not we consume it, those are all the same. But the emits between them have different parameters, right? We would just be able to say, well, set up a second code somewhere and have like a thing that says when we go to do an emit, look and see if that code clarifies. So we could change the emit to like emit parameterized or emit table lookup or something, and use a secondary state code that remembers which of these sub things we're in. Now that's a bit specific, and how it works out really depends on which thing we're generating. So like I said, we don't want to go down that road just now, but just looking at this, that's the next thing that's popping out to me, is that we probably have a lot of opportunities to basically do stuff like what the flag does, to turn states that look almost identical into states that are the same state by storing other state information besides the main state of the state machine as like separate variables that get optimized differently, right? But anything we add like that also adds the possibility of complicating the problem if we're not careful about how we do it. So we don't want to just jump into that. That's more of a back-end optimization than a front-end optimization, I think. Because it depends on which one we're doing. But the optimizations we've applied so far are strict optimizations to any state machine, right? We've gotten the state number down, we've gotten the transition number down, we've done nothing to pessimize either of those situations. So I'm pretty confident that we can figure out what back-ends use independently of whether or not these get applied. These should always get applied, I guess is what I'm trying to say. So I want to take the last few minutes of this episode to peruse through our new state machine. It's a lot different than the one I wrote by hand now. I'll just show you. So like here I have my list of operators, and that list of operators gets turned into, if I come down here, main ops, where is that? Main ops without dot or slash. So these things here, colon forward all the way to comma, those things are not actually present in the original state machine. The original state machine says if you see any of these individual characters, go to the operator state. And the operator state is generated by this function call here. And this function call here then made all this code that actually now gets optimized into a thing where root actually has each of these states and no operator state. The operator state is gone. And that's really neat to me. That's just so much fun. So now each of these is hand-coded right into the root, and so our root handler can, you know, do whatever it wants to do. It can build lookup table for this if it says like, hey, each of these individual things has a different transition rule. So even if it's a control flow thing, maybe for operators in particular, it would have a rule that's like, if we see any of these, transition to that. so on. So that's going to get to kind of this question of like, can we do isolations? How well can we do isolations of the state machine? What do I mean by isolations? What can we get for doing them? And start to design how this thing works. And it might be, now that I'm talking it through in this thought process here, that it's a little more intricate than what I originally have proposed in the to-do list, because there's a good chance that we find ways to isolate some parts of the state machine and drive them with really good lookup table loops, and other parts are harder to isolate, and therefore we do them with control flow states, and we kind of have a hybrid system that tries to drop down to tables wherever it can, get a really nice small table, but anywhere where it can't do that, it will operate as a control flow state machine so that it can flow into a table wherever it needs to, right? And have the flexibility of procedural code anywhere that it can't figure out how to do that. It's going to be kind of a neat part of this project. It's totally separate from everything we've done so far, but I think this is it. I think we've optimized the state machine well within to a satisfactory range for me. 65 states is bigger than any state machine I've ever built for a Lexer, but that's because I haven't manually done any isolating. In my previous state machines, I had it down to more like, I think, 30. But I was manually handling a lot of stuff that I'm not manually handling anymore in the way those were ruled. And it might have been more than 30 anyway, I'm not sure. It might have, like, for instance, it was doing these string prefixing and stuff, and that's tricky stuff to do, but I think that, like, it had, like, hand-rolled tricks inside the identifier state rather than having separate states for each prefix of the string and stuff like that. That just made it fairly hard to actually modify it because it was not, like, defined cleanly in one spot. It was spread across a table generator that was generating separate tables for isolated cases, one for the preprocessor states, one for the non-preprocessor states, which here are all rolled into one machine with flags. It had all these, like, the operator stuff is all the same, but it had like assumptions about white space and stuff that this doesn't have, so this is doing more work to parse white space as an actual state, whereas that didn't treat white space as a state, and was hand-rolled separately, and so on and so on, right? A lot of stuff. But yeah, this is pretty neat. You can see that in most cases we consume, and the only cases we tend to not have a consume is the go to root part. It's very uncommon now to find a consume, or a transition handler that does not consume, except for the ones that do go to root. So there might be a way to optimize that, right? We might be able to do a specialized thing that's like how to deal with that, but really, that's just, again, that's actually more of a, whether or not we do that has a lot more to do with how we're going to generate it. This is the right thing to do if we're doing a fully control flow based system. So I don't want to get into thinking about optimizing that. The way to optimize it if it's control flow is to just say this literally is a go-to. That way the big complicated root handler only needs to exist once, and it is just like a thing you can jump to and reuse from anywhere. If you're uncomfortable with the idea that we're not doing the consume here, that won't really matter in that case, because we aren't driving this from a lookup table, so we're actually going to consume it by just doing the control flow into there. It's if we are going to do a lookup table for everything that we suddenly don't want this consume to be a variable, because then we have to use a lookup table to determine whether or not we do a consume, and that's less cool. So if we were going to try to optimize out this go to root for lookup table purposes, what we would basically end up doing is just saying copy forward go to root the same way we did here, replace this with this. Yeah, actually, so this thing, remove peaks into single entry point states, is pretty close to what we need for the whole thing. The only difference is, by doing it only for single entry point states, we guaranteed that the number of transitions wouldn't grow, but we could totally have a thing that's like, do the same logic on every possible transition that doesn't have a consume, and what we would have at the end of that process would essentially be at least one layer of a system that does totally get rid of all the non-consume paths. The only thing about that wouldn't work is that only does one layer. So if anyone ever peeks into a state that also does a peak and they pulled that peak forward, you'd have to apply this several times until you weren't getting any more optimizations, right? But for now, I'm pretty happy with all this. This has been a pretty good. Now that we have that, getting that set theory stuff down correctly in the other episodes has let the last few episodes be mostly about optimizing the state machine the way I kind of wanted to, with the exception of doing this because I decided that this should wait, and that's a pretty good result, I think. Pretty good result. Still wondering if there isn't anything else that can be done. Why is there an 8 here? Ah, because U8. So when you see a U8, that's a perfect prefix. So neat, so neat. Here's a state handler that depends on the flag there, whether it includes this character or that character, which looks really cool. Here we're figuring out if we're entering into an octal state. Consume, consume, consume. Here we see an emit before consume, which means that this got pulled forward. This must have been a new line character, I guess. So here we have some pretty interesting stuff that works a lot like root. So in that concept of isolating things, we can see here there's a lot of people who go to string without doing a consume. Like fallback for this one is a string, the fallback for this one is a string, the fallback for this one is a string. So there's like all these different things. It's like if it fails to do what we expect, go back to string. And that's a pretty good candidate for careful inspection and thought, because that means there's kind of the set of states that all loop in on each other, and so they tend to stay within a cluster, right? There's a lot of ways to transition around that doesn't leave that cluster, and that's kind of what isolation will be about, is like an isolated section will be one where we can find a set of states such that when you're inside that set of states, the number of transitions that you can reach from that set of states, right, we can list out all those transitions and say how many of them leave the cluster and how many of them don't. And if the ratio is really good, right, there's a very small number that leave the cluster and a very high number that don't leave the cluster, then you have a really good case to isolate that section into a sub-state machine that is table-driven, and say when you want to enter that state, the way you do it, when you want to enter that cluster, you start doing this table loop, and then you have a few cases in that table loop that eventually can break you out of the table loop and say, ah, this is a transition out of this cluster, right? And that's what the isolation would be like. Go to string again. Yep, all of these. So this 5, 4, all of this could get isolated so nicely to cut down, and it would be like the string state machine would then be like something like maybe 10 or 15 or 20 states by itself, and that's a really small number. That's a really ideal number for a lookup table. And then you would isolate those out so that the rest of the state machine is now like split into this portion and that portion. The portion, if we ever got it down to the point where every single sub portion was small enough, you would just have every single state represented as a part of one of these isolated pieces. But it might not get that far. It might be like root is never that way, perhaps, and root is always a control flow node on the state machine. I don't know. It's a lot of fun stuff to play with in the next episode. I'm just kind of getting some ideas while we wrap up here. But I should close the episode down rather than rambling and thinking about these things. So thanks so much for checking this out. I'm having a really good time. Hope you are too. And we'll be doing more episodes, on schedule, hopefully. Later. Bye.